Learning objectives. In this chapter, the user will learn the following in detail. Mathematics for algorithmic sets, functions, relations, vectors and matrices, linear inequalities and linear equations. Review of basic concepts, worst case and average case analysis, big O notations, small o notations, omega notations, theta notations, solving recurrence equations. Asymptotic notation. The notations used to describe the asymptotic running time of an algorithm are defined in terms of functions whose domains are the set of natural numbers capital N equal to 0, 1, 2 and so on. Such notations are convenient for describing the worst case running time function T of n, which usually is defined only on integer input sizes. Big O notation. When we have only an asymptotic upper bound, use big O notation. For a given function g of n, we denote by big O of g of n, the set of functions. Big O of g of n equal to f of n such that there exist positive constants c and n naught such that 0 less than or equal to f of n less than or equal to cg of n for all n greater than or equal to n naught. Use big O notation to give an upper bound on a function to within a constant factor. This figure shows the big O notation gives an upper bound for a function to within a constant factor. We can write f of n equal to big O of g of n if there are positive constants n naught and c such that at and to the right of n naught the value of f of n always lies on or below cg of n. F of n equal to big O of g of n to indicate that a function f of n is a member of the set big O of g of n. Note that f of n equal to big theta of g of n implies f of n equal to big O of g of n, since big theta notation is a stronger notion than big O notation. Written set theoretically, big theta of g of n is a subset of big O of g of n. Thus, a proof that any quadratic function a n squared plus b n plus c where a greater than 0 is in big theta of n square also shows that any such quadratic function is in big O of n square. What may be more surprising is that when a greater than 0, any linear function a n plus b is in big O of n square, which is easily verified by taking c equal to a plus mod b and n naught equal to max of 1 comma minus b by a. Using big O notation, we can often describe the running time of an algorithm merely by inspecting the algorithm's overall structure. For example, the doubly nested loop structure of the insertion sort algorithm yields an big O of n square upper bound on the worst case running time. The cost of each iteration on the inner loop is bounded from above by big O of 1 constant. The indices I and j are both at most n and the inner loop is executed at most once for each of the n squared pairs of values for I and j. Since big O notation describes an upper bound, when we use it to bound the worst case running time of an algorithm, we have a bound on the running time of the algorithm on every input. Thus, the big O of n square bound on worst case running time of insertion sort also applies to its running time on every input. The big theta of n square bound on the worst case running time of insertion sort, however, does not imply a big theta of n square bound on the running time of insertion sort on every input. For example, when the input is already sorted, insertion sort runs in big theta of n time. Small o notation. The asymptotic upper bound provided by big O notation may or may not be asymptotically tight. The bound 2n square equal to big O of n square is asymptotically tight, but the bound 2n equal to big O of n square is not. Use small o notation to denote an upper bound that is not asymptotically tight. Formally define small o of g of n as the set small o of g of n equal to f of n such that for any positive constant c greater than 0, there exists a constant n naught greater than 0 such that 0 less than or equal to f of n less than cg of n for all n greater than or equal to n naught. For example, 2n equal to small o of n square, but 2n square not equal to small o of n square. The definitions of big O notation and small o notation are similar. The main difference is that in f of n equal to big O of g of n, the bound 0 less than or equal to f of n less than or equal to cg of n holds for some constant c greater than 0. But in f of n equal to small o of g of n, the bound 0 less than or equal to f of n less than cg of n holds for all constants c greater than 0. Intuitively, in small o notation, the function f of n becomes insignificant relative to g of n as n approaches infinity. That is, limit n approaches infinity, f of n over g of n equal to 0. Big omega notation. Big omega notation provides an asymptotic lower bound. For a given function g of n, denote by big omega of g of n the set of functions big omega of g of n equal to f of n such that there exist positive constants c and n naught, such that 0 less than or equal to cg of n less than or equal to f of n for all n greater than or equal to n naught. This figure shows the intuition behind big omega notation. For all values n at or to the right of n naught, the value of f of n is on or above cg of n. The running time of an algorithm is big omega of g of n. The running time on that input is at least a constant time g of n for sufficiently large n. Equivalently, giving a lower bound on the best case running time of an algorithm. For example, the best case running time of insertion sort is big omega of n. The running time of insertion sort, therefore, belongs to both big omega of n and big O of n square, since it falls anywhere between a linear function of n and a quadratic function of n. Moreover, these bounds are asymptotically as tight as possible. For instance, the running time of insertion sort is not big omega of n square, since there exists an input for which insertion sort runs in big theta of n time. Example, when the input is already sorted. It is not contradictory, however, to say that the worst case running time of insertion sort is big omega of n square, since there exists an input that causes the algorithm to take big omega of n square time. Little omega notation. Use little omega notation to denote a lower bound that is not asymptotically tight. One way to define it is by f of n belongs to little omega of g of n if and only if g of n belongs to small o of f of n. Define little omega of g of n as the set little omega of g of n is equal to f of n such that for any positive constant c greater than 0, there exists a constant n naught greater than 0, such that 0 less than or equal to cg of n less than f of n for all n greater than or equal to n naught. For example, n squared by 2 equal to little omega of n, but n squared by 2 not equal to little omega of n square. The relation f of n equal to little omega of g of n implies that limit n approaches infinity, f of n over g of n equal to infinity. If the limit exists, that is, f of n becomes arbitrarily large relative to g of n as n approaches infinity. Theta notations. For a given function g of n, we denote by big theta of g of n the set of functions theta of g of n equal to f of n such that there exist positive constants c1, c2 and n0 such that 0 less than or equal to c1 g of n, less than or equal to f of n, less than or equal to c2 g of n, for all n greater than or equal to n0. This figure gives an intuitive picture of functions f of n and g of n, where f of n equal to theta of g of n if there exist positive constants n0, c1 and c2. Theta notation bounds a function to within constant factors. For all values of n at and to the right of n0, the value of f of n lies at or above c1 g of n and at or below c2 g of n. In other words, for all n greater than or equal to n0, the function f of n is equal to g of n to within a constant factor. G of n is an asymptotically tight bound for f of n. A function f of n belongs to the set theta of g of n if there exist positive constants c1 and c2 such that it can be sandwiched between c1 g of n and c2 g of n for sufficiently large n. Because theta of g of n is a set, we would write f of n belongs to theta of g of n to indicate that f of n is a member of theta of g of n. Instead, usually write f of n equal to theta of g of n to express the same notion. The definition of theta of g of n requires that every member f of n belongs to theta of g of n be asymptotically non-negative, that is, that f of n be non-negative whenever n is sufficiently large. An asymptotically positive function is one that is positive for all sufficiently large n. Consequently, the function g of n itself must be asymptotically non-negative, or else the set f of n belongs to theta of g of n is empty. Assume that every function used within theta notation is asymptotically non-negative. Linear inequalities and linear equations. Linear inequalities. The term inequality is applied to any statement involving one of the symbols greater than, less than or equal to, greater than or equal to. Example of inequalities are x greater than or equal to 1, x plus y plus 2z greater than 16, p squared plus q squared less than or equal to 1 by 2, a squared plus ab greater than 1. Fundamental properties of inequalities. If a less than or equal to b and c is any real number, then a plus c less than or equal to b plus c. For example, minus 3 less than or equal to minus 1 implies minus 3 plus 4 less than or equal to minus 1 plus 4. If a less than or equal to b and c is positive, then ac less than or equal to bc. For example, 2 less than or equal to 3 implies 2 into 4 less than or equal to 3 into 4. If a less than or equal to b and c is negative, then ac greater than or equal to bc. For example, 3 less than or equal to 9 implies 3 into minus 2 greater than or equal to 9 into minus 2. If a less than or equal to b and b less than or equal to c, then a less than or equal to c. For example, minus 1 by 2 less than or equal to 2 and 2 less than or equal to 8 by 3 imply minus 1 by 2 less than or equal to 8 by 3. Solution of inequality. By solution of the one variable inequality 2x plus 3 less than or equal to 7, we mean any number which substituted for x yields a true statement. For example, 1 is a solution of 2x plus 3 less than or equal to 7, since 2 into 1 plus 3 equal to 5 and 5 is less than and equal to 7. By a solution of two variable inequality x minus y less than or equal to 5, we mean any ordered pair of numbers which when substituted for x and y respectively yields a true statement. For example, 2, 1 is a solution of x minus y less than or equal to 5 because 2 minus 1 equal to 1 and 1 less than or equal to 5. By a solution of three variable inequality 2x minus y plus z greater than or equal to 3, we means an ordered triple of number which when substituted for x, y and z respectively yields a true statement. For example, 2, 0, 1 is a solution of 2x minus y plus z greater than or equal to 3. A solution of inequality is said to satisfy the inequality. For example, 2, 1 is satisfy x minus y less than or equal to 5. Two or more inequalities, each with the same variables considered as a unit, are said to form a system of inequalities. For example, x greater than or equal to 0, y greater than or equal to 0, 2x plus y greater than or equal to 4. A system of inequalities, each of whose members is linear, is said to be a system of linear inequalities. Geometric interpretation of inequalities. An inequality in two variable x and y describes a region in the xy plane called its graph, namely the set of all points whose coordinates satisfy the inequality. The y-axis divide the xy plane into two regions called half planes. Right half plane, the region of points whose coordinates satisfy inequality x greater than 0. Left half plane, the region of points whose coordinates satisfy inequality x less than 0. Similarly, the x-axis divides the xy plane into two half planes. Upper half plane, in which inequality y greater than 0 is true. Lower half plane, in which inequality y less than 0 is true. What is x-axis and y-axis? They are simply lines. So, the above arguments can be applied to any line. Every line ax plus by equal to c divides the xy plane into two regions called its half planes. On one half plane ax plus by greater than c is true. On the other half plane ax plus by less than c is true. Linear equations. One unknown. A linear equation in one unknown can always be stated into the standard form ax equal to b, where x is an unknown and a and b are constants. If a is not equal to 0, this equation has a unique solution. X is equal to b by a. Two unknowns. A linear equation in two unknown x and y can be put into the form ax plus by equal to c, where x and y are two unknowns and a, b, c are real numbers. Also, we assume that a and b are no zero. Solution of linear equation. A solution of the equation consists of a pair of numbers u equal to k1, k2, which satisfies the equations ax plus by equal to c. Mathematically speaking, a solution consists of u equal to k1, k2 such that a k1 plus b k2 equal to c. Solution of the equation can be found by assigning arbitrary values to x and solving for y, or assigning arbitrary values to y and solving for x. Geometrically, any solution u equal to k1, k2 of the linear equation ax plus by equal to c determine a point in the Cartesian plane. Since a and b are not zero. The solution U correspond precisely to the points on a straight line. Two equations in the two unknowns. A system of two linear equations in the two unknowns x and y is a1x plus b1x equal to c1, a2x plus b2x equal to c2, where a1, a2, b1, b2 are not zero. A pair of numbers which satisfies both equations is called a simultaneous solution of the given equations or a solution of the system of equations. Geometrically, there are three cases of simultaneous solution. 1. If the system has exactly one solution, the graph of the linear equations intersect in one point. 2. If the system has no solutions, the graphs of the linear equations are parallel. 3. If the system has an infinite number of solutions, the graphs of the linear equations coincide. The special cases 2 and 3 can only occur when the coefficient of x and y in the two linear equations are proportional. a1 by a2 is equal to b1 by b2 implies a1 b2 minus a2 b1 is equal to 0. Implies matrix a1 b1 a2 b2 is equal to 0. The system has no solution when a1 by a2 is equal to b1 by b2 is not equal to c1 by c2. The solution to system a1x plus b1x equal to c1, a2x plus b2x equal to c2 can be obtained by the elimination process, whereby reduce the system to a single equation in only one unknown. This is accomplished by the following algorithm. Algorithm. Step 1. Multiply the two equations by two numbers which are such that the resulting coefficients of one of the unknown are negative of each other. Step 2. Add the equations obtained in step 1. The output of this algorithm is a linear equation is one unknown. This equation may be solved for that unknown and the solution may be substituted in one of the original equations yielding the value of the other unknown. As an example, consider the following system. 3x plus 2y equal to 8, which can be represented as equation 1. 2x minus 5y equal to minus 1 can be represented as equation 2. Step 1. Multiply equation 1 by 2 and equation 2 by minus 3. 6x plus 4y equal to 16 minus 6x plus 15y equal to 3. Step 2. Add equations output of step 1. 19y equal to 19. Thus, we obtain an equation involving only unknown y. We solve for y to obtain y equal to 1. Next, we substitute y equal to 1 in equation 1 to get x equal to 2. Therefore, x equal to 2 and y equal to 1 is the unique solution to the system. N equations in n unknowns. Now consider a system of n linear equations in n unknowns. a11x1 plus a12x2, it goes up to a1nxn is equal to b1. a21x1 plus a22x2 goes up to a2nxn is equal to b2. It goes up to an1x1 plus an2x2 plus, and it goes up to annxn is equal to bn, where the aij, bi are real numbers. The number aij is called the coefficient of xj in the ith equation, and the number bi is called the constant of the ith equation. A list of values for the unknowns: x1 equal to k1, x2 equal to k2, and it goes up to xn equal to kn. Or, equivalently, a list of n numbers. U equal to k1, k2 up to kn is called a solution of the system if, with kg substituted for xg, the left-hand side of each equation in fact equals the right-hand side. The above system is equivalent to the matrix equation which is shown here. Or simply we can write Ax equal to B, where A equal to Aij, X equal to Xi, and B equal to Bi. The matrix which is shown here is called the coefficient matrix of the system of n linear equations in the system of n unknown. The matrix which is shown here is called the augmented matrix of n linear equations in n unknown. Solution of a triangular system. If Aij equal to 0 for I greater than j, then system of n linear equations in n unknown assumes the triangular form. N linear equations in n unknown is shown here, where mod A equal to A11, A22 up to ANN. If none of the diagonal entries A11, A22 up to ANN is 0, the system has a unique solution. Back substitution method. We obtain the solution of triangular system by the technique of back substitution. Consider the above general triangular system. First, we solve the last equation for the last unknown xn. Xn equal to bn by ann. Second, we substitute the value of xn in the next to last equation and solve it for the next to last unknown xn minus 1. Xn minus 1 is equal to bn minus 1 minus an minus 1 comma n bn by ann by an minus 1 comma n minus 1. Third, we substitute these values for xn and xn minus 1 in the third from last equation and solve it for the third from last unknown xn minus 2 is shown here. In general, we determine xk by substituting the previously obtained values of xn, xn minus 1, it goes up to xk plus 1 in the kth equation. Xk is equal to bk minus summation of n minus k plus 1 to n akm xm by akk. Gaussian elimination. Gaussian elimination is a method used for finding the solution of a system of linear equations. This method consists of two parts. This part consists of step-by-step putting the system into triangular system. This part consists of solving the triangular system by back substitution. X minus 3y minus 2z equal to 6, equation 1. 2x minus 4y plus 2z equal to 18, equation 2. Minus 3x plus 8y plus 9z equal to minus 9, equation 3. First part, eliminate first unknown x from the equations 2 and 3. A. Multiply minus 2 to equation 1 and add it to equation 2. Equation 2 becomes 2y plus 6z equal to 6. B. Multiply 3 to equation 1 and add it to equation 3. Equation 3 becomes minus y plus 3z equal to 9. And the original system is reduced to the system x minus 3y minus 2z equal to 6. 2y plus 6z equal to 6. Minus y plus 3z equal to 9. Now we have to remove the second unknown y from new equation 3 using only the new equations 2 and 3. Multiply equation 2 by 1 by 2 and add it to equation 3. The equation 3 becomes 6z equal to 12. Therefore, our given system of 3 linear equations of 3 unknown is reduced to the triangular system. x minus 3y minus 2z equal to 6. 2y plus 6z equal to 6. 6z equal to 12. Second part. In the second part, we solve the equation by back substitution and we get x equal to 1, y equal to minus 3, z equal to 2. In the first stage of algorithm, the coefficient of x in the first equation is called the pivot. And in the second stage of algorithm, the coefficient of y in the second equation is the point. Clearly, the algorithm cannot work if either pivot is 0. In such a case, one must interchange equation so that pivot is not 0. In fact, if one would like to code this algorithm, then the greatest accuracy is attained when the pivot is as large in absolute value as possible. For example, we would like to interchange equation 1 and equation 2 in the original system in the above example before eliminating x from the second and third equation. That is, first step of the algorithm transfer system as 2x minus 4y plus 2z equal to 18. X minus 4y plus 2z equal to 18. Minus 3x plus 8y plus 9z equal to minus 9. Determinants and systems of linear equations. Consider a system of n linear equations in n unknowns. That is, for the following system, which is shown here. Let D denote the determinant of the matrix A plus Aij of coefficients, that is, let D equal to modulus of A. Also, let Ni denote the determinants of the matrix obtained by replacing the ith column of A by the column of constants. Theorem: if D not equal to 0, the above system of linear equations has the unique solution U equal to n1 by D, n2 by D up to nn by D. This theorem is widely known as Cramer's rule. It is important to note that Gaussian elimination is usually much more efficient for solving systems of linear equations than is the use of determinants. Mathematics for algorithmic functions. Given two sets A and B, a function f is a binary relation of A and B such that for all A belongs to set A, there exists precisely one B belongs to set B such that within parenthesis A, B belongs to F. The set A is called the domain of F and the set B is called the codomain of F. We sometimes write F such that A implies B, and if A, B belongs to F, we write B is equal to F of A, since B is uniquely determined by the choice of A. Intuitively, the function f assigns an element of B to each element of A. No element of A is assigned two different sets of B, but the same element of B can be assigned to two different elements of A. For example, the binary relation f is equal to, within set symbols, within parenthesis A, B such that A, B belongs to n and B is equal to A mod 2 is a function f such that n implies the set 0 and 1. Since for each natural number A, there is exactly one value B in 0, 1 such that B is equal to A mod 2. For this example, 0 is equal to f of 0, 1 is equal to f of 1, 2 is equal to f of 2, etc. In contrast, the binary relation G equal to, within set symbols, within parenthesis A, B such that A, B belongs to n and A plus B is even, is not a function. Since 1, 3 and 1, 5 are both in G, and thus for choice A equal to 1, there is not precisely one B such that A comma B belongs to G. For given function f such that A implies B, if B is equal to f of A is the argument of f and that B is the value of f at A. We can define a function by stating its value for every element of its domain. For example, we might define f of n is equal to 2n for n belongs to capital N, which means f is equal to within set symbols within parenthesis n comma 2n such that n belongs to capital N. Two functions f and g are equal if they have the same domain and codomain, and if for all A in the domain f of A equal to g of A. A finite sequence of length n is a function f whose domain is the set of n integers 0, 1 up to n minus 1. We often denote a finite sequence by listing its values f of 0, f of 1 up to f of n minus 1. An infinite sequence is a function whose domain is the set n of natural numbers. For example, the Fibonacci sequence 0, 1, 1, 2, 3, 5, 8, 13, 21, and so on. When the domain of a function f is a Cartesian product, omit the extra parenthesis surrounding the argument of f. For example, if we had a function f such that a1 cross a2 cross up to an implies b, we write b equal to f of a1, a2 up to an. Each ai an argument to the function f, though technically the single argument to the function f is the n tuple a1, a2 up to an. If f such that a implies b is a function and b equal to f of a, then sometimes say that b is the image of a under f. The image of a set a dash is a subset of set a under f is defined by f of a dash is equal to within set b belongs to set b such that b is equal to f of a for some a belongs to set a dash. The range of f is the image of its domain, that is f of a. For example, the range of the function f such that n implies n, defined by f of n equal to 2n, is f of n is equal to within set symbols m such that m equal to 2n for some n belongs to capital N, the set of non-negative even integers. A function is a surjection if its range in its codomain. For example, the function f of n, the floor of n by 2 is a surjective function from n to n, since every element in capital N appears as the value of f for some argument. In contrast, the function f of n equal to 2n is not a surjective function from n to n, since no argument to f can produce 3 as a value. The function f of n equal to 2n is, however, a surjective function from the natural numbers to the even numbers. A surjection f such that a implies b is sometimes described as mapping a onto b. When we say that f is onto, we mean that it is surjective. A function f such that a implies b is an injection if distinct arguments to f produce distinct values. That is, a is not equal to a dash implies f of a not equal to f of a dash. For example, the function f of n equal to 2n is an injective function from n to n. Since each even number b is the image under f of at most one element of the domain, namely b by 2. The function f of n is equal to floor of n by 2 is not injective since the value 1 is produced by two arguments, 2 and 3. An injection is sometimes called a one-to-one function. A function f such that a implies b is a bijection if it is injective and surjective. For example, the function f of n is equal to minus 1 the whole power n, ceiling of n by 2 is a bijection from n to z. 0 implies 0, 1 implies minus 1, 2 implies 1, 3 implies minus 2, and so on. The function is injective since no element of z is the image of more than one element of n. It is surjective since every element of z appears as the image of some element of n. Hence, the function is bijective. A bijection is sometimes called a one-to-one correspondence since it pairs elements in the domain and codomain. A bijection from a set A to itself is sometimes called a permutation. When a function is bijective, we define its inverse, f inverse, as f inverse of b equal to a, if and only if f of a equal to b. For example, the inverse of the function f of n equal to minus 1 power n, the ceiling of n by 2, is f inverse of m equal to 2m if m greater than or equal to 0, minus 2m minus 1 if m less than 0. Mathematics for algorithmic relations. A binary relation R on two sets A and B is a subset of the Cartesian product A cross B. If A, B belongs to R, we sometimes write A, R, B. When we say that R is a binary relation on set A, we mean that R is a subset of A cross A. For example, the less than relation on the natural number is the set A, B such that A, B belongs to n and A less than B. An n-ary relation on sets A1, A2 up to An is a subset of A1 cross A2 cross up to An. A binary relation R is a subset of A cross A is reflexive if A or A for all A belongs to set A. For example, equals and less than or equal to are reflexive relation on n, but less than is not. The relation R is symmetric if A or B implies B or A for all A, B belongs to set A. For example, equal to is symmetric, but less than and less than or equal to are not symmetric. The relation R is transitive if A or B and B or C imply A or C for all A, B, C belongs to set A. For example, the relations less than or equal to and equal to are transitive, but the relation R is equal to A, B such that A and B belongs to set N and A equal to B minus 1 is not, since 3 or 4 and 4 or 5 do not imply 3 or 5. A relation that is reflexive, symmetric and transitive is an equivalence relation. For example, equal to is an equivalence relation on the natural numbers, but less than is not. If R is an equivalence relation on a set A, then for A belongs to set A, the equivalence class of A is the set A equal to B belongs to set A such that A or B, that is, the set of all elements equivalent to A. For example, we define R is equal to A, B such that A comma B belongs to set n and A plus B is an even number, then R is an equivalence relation since A plus A is even reflexive. A plus B is even implies B plus A is even symmetric, and A plus B is even and B plus C is even imply A plus C is even transitive. A binary relation R on a set A is antisymmetric if A or B and B or A imply A equal to B. For example, the less than or equal to relation on the natural numbers is antisymmetric since A less than or equal to B and B less than or equal to A imply A equal to B. A relation that is reflexive, antisymmetric and transitive is a partial order, and we call a set on which a partial order is defined as partially ordered set. For example, the relation is a descendant of is a partial order on the set of all people if we view individuals as being their own descendants. In a partially ordered set A, there may be no single maximum element such that B or A for all B belongs to set A. Instead, the set may contain several maximal elements A such that for no B belongs to set A, where B is not equal to A, is it the case that A or B? For example, a collection of different sized boxes may contain several maximal boxes that don't fit inside any other box, yet it has no single maximum box into which any other box will fit. A relation R on a set A is a total relation if for all A, B belongs to set A. We have A or B or B or A or both, that is, if every pairing of elements of A is related by R. A partial order that is also a total relation is a total order or linear order. For example, the relation less than or equal to is a total order on the natural numbers, but the is a descendant of relation is not a total order on the set of all people, since there are individuals neither of whom is descended from the other. A total relation that is transitive but not necessarily reflexive and antisymmetric is a total preorder. Mathematics for algorithmic sets. Sets. A set is a collection of different things or distinct objects represented as a unit. The objects in a set are called its elements or members. If an object X is a member of a set S, we write X belongs to S. If X is not a member of S, we write X does not belongs to S. A set cannot contain the same object more than once, and its elements are not ordered. For example, consider the set S, which has the elements 7, 21 and 57. Then 7 belongs to 7, 21 and 57 set, and 8 does not belongs to this set, or equivalently, 7 belongs to S and 8 does not belongs to S. We can also describe a set containing elements according to some rule. We can write this in the below format. Within set symbol n such that rule about n. For example, within set symbol n such that n equal to m square for some m belongs to capital N. Here this set represents a set of perfect squares and capital N represents natural numbers. Within set notation, a colon indicates such that. Set cardinality. The number of elements in a set is called cardinality or size of the set, denoted modulus of S or n of S. The two sets have same cardinality if their elements can be put into a one-to-one correspondence. It is easy to see that the cardinality of an empty set is 0, that is modulus of 5. Multiset. If we want to take the number of occurrences of members into account, we call the group a multiset. For example, 7 and 7, 7 are identical as set, but 7 and 7, 7 are different as multiset. Infinite set. A set contains infinite elements is called infinite set. For example, set of negative integers, set of integers, etc. Empty set. A set does not have any members is called an empty set. It is denoted as phi or the set symbols without any members. Subset. For two sets A and B, we say that A is a subset of B, written like this: if every member of A also is a member of B. Formally, A is a subset of B if X belongs to A implies X belongs to B, written as shown. Proper subset. Set A is a proper subset of B, written A proper subset symbol and B. If A is a subset of B and not equal to B, that is, set A is proper subset of B. If A is subset of B, but set A is not equal to set B. Equal sets. The sets A and B are equal, written A equal to B, if each is a subset of the other. Let A and B be sets. Set A equal to set B if A is subset of B and B is subset of A. Power set. Let A be the set. The power of A, written as P of A or 2 power A, is the set of all subsets of A. That is, P of A is equal to, within set symbol, B such that B is a subset of A. For example, consider the set A which has the elements 0 and 1. The power set of A which has the subsets empty set 0, 1, 0 and 1. And the power set of A is the set of all pairs, two tuples is called pairs, whose elements are 0 and 1 has the subsets 0, 0, 0, 1, 1, 0 and 1, 1. Disjoint sets. Let A and B be sets. A and B are disjoint if A intersection B is equal to null. Union of sets. The union of A and B are written A union B is the set we get by combining all elements in A and B into a single set, that is, A union B which has the elements X such that X belongs to A or X belongs to B. For two finite sets A and B, we have identity modulus of A union B is equal to modulus of A plus modulus of B minus modulus of A intersection B. We can conclude modulus of A union B less than or equal to modulus of A plus modulus of B. That is, if modulus of A intersection B is equal to 0, then modulus of A union B is equal to modulus of A plus modulus of B. And if A is a subset of B, then mod A less than or equal to mod B. Intersection sets. The intersection of set A and set B, written A intersection B, is the set of elements that are both in A and in B. That is, A intersection B is equal to X such that X belongs to A and X belongs to B. Difference of sets. Let A and B be sets. The difference of set A and set B is A minus B is equal to, within set symbol, X such that X belongs to A and X not belongs to B. For example, let A contains 1, 2 and 3 and set B contains 2, 4, 6 and 8. The set difference A minus B is equal to 1, 3, while B minus A is equal to 4, 6 and 8. Complement of a set. All sets under consideration are subset of some large set U, which is called universal set. Given a universal set U, the complement of A is written as A dash. That is, set of all elements under consideration that are not in A. Formally, let A be a subset of universal set U. The complement of A in U is A dash equal to U minus A, or A dash is equal to, within set symbol, X such that X belongs to U and X does not belongs to A. For any set A is a subset of U, we have following rules or laws. A double dash is equal to A. A intersection A dash is equal to null or phi. A union A dash is equal to universal set, which is represented as U. Symmetric difference O plus or XR plus. Let A and B be sets. The symmetric difference of A and B is A O plus B is equal to within set symbol X such that X belongs to A or X belongs to B but not both. Therefore, A O plus B equal to A union B minus A intersection B. For example, let us take two sets A and B. Set A contains 1, 2 and 3 and set B contains 2, 4, 6 and 8. The symmetric difference A circle plus B equal to within set symbol 1, 3, 4, 6 and 8. Sequences. A sequence of objects is a list of objects in some order. For example, the sequence 7, 21 and 57 would be written as within parentheses 7, 21 and 57. In a set the order does not matter, but in a sequence it does. Hence, within parentheses 7, 21 and 57 is not equal to within curly braces 57, 7 and 21. Repetition is not permitted in a set, but repetition is permitted in a sequence. So, 7, 7, 21 and 57 which is represented within parentheses is different from 7, 21 and 57 which is represented within curly braces. Tuples. Finite sequence often are called tuples. For example, within parentheses 7 and 21 is called 2 tuple or 2 pair. Within parentheses 7, 21 and 57 is called 3 tuple. And like that 7, 21 goes up to k represented as k tuple. An ordered pair of two elements A and B is denoted within parentheses A, B and can be defined as within parentheses A, B is equal to open parentheses A, open curly braces, A, B, then close curly brace, then close parenthesis. Cartesian product or cross product. If A and B are two sets, the cross product of A and B written A cross B is the set of all pairs wherein the first element is a member of the set A and the second element is a member of the set B. Formally, A cross B equals within set symbols within parentheses A, B such that A belongs to set A, B belongs to set B. For example, let set A contains the elements 1 and 2 and set B contains the elements X, Y and Z. Then A cross B is equal to within set symbols it has some subsets 1, X, 1, Y, 1, Z, 2, X, 2, Y and 2, Z. When A and B are finite sets, the cardinality of their product is modulus of A cross B is equal to mod A and mod B. N tuples. The Cartesian product of n sets A1, A2 goes up to An is the set of n tuples. A1 cross A2 cross it goes up to An is equal to within set symbols A1 up to An such that Ai belongs to the set Ai. Here I represents 1, 2 and up to n, whose cardinality is modulus of A1 cross A2 cross it goes up to An is equal to mod A1 and mod A2 it goes up to mod An. If all sets are finite, we denote an n-fold Cartesian product over a single set A by the set A power n is equal to A cross up to cross A, whose cardinality is modulus of A power n is equal to modulus of A the whole power n if A is finite. Set operations obey the following laws. Empty set laws. A intersection null is equal to null. A union null is equal to A. Idempotency laws. A intersection A is equal to A. A union A is equal to A. Commutative laws. A intersection B is equal to B intersection A. A union B is equal to B union A. Associative laws. A intersection of B intersection C is equal to A intersection B intersection C. A union of B union C is equal to A union B union C. Distributive laws. A intersection of B union C is equal to A intersection B union A intersection C. A union of B intersection C is equal to A union B intersection A union C. Absorption laws. A intersection of A union B is equal to A. A union of A intersection B is equal to A. De Morgan's laws. A minus B intersection C is equal to A minus B union A minus C. A minus B union C is equal to A minus B intersection A minus C. Review of basic concepts in algorithms. Algorithm is defined as it is a set of rules for carrying out calculation either by hand or on a machine. It is a finite step-by-step instructions to achieve a required result. It is a sequence of computational steps that transform the input into the output. It is a sequence of operations performed on data that have to be organized in data structures. It is an abstraction of a program to be executed on a physical machine model of computation. Two desired properties of algorithms. Correctness always provides correct output when presented with legal input. Example, traveling salesperson problem. Input, a sequence of n cities with the distances dij between each pair of cities. Output, a permutation ordering of the cities C1 to Cn that minimizes the expression summation of j equal to 1 to n minus 1 dj dash, j dash plus 1 plus dn dash, 1 dash. Which of the following algorithms is correct? Nearest neighbor, initialize 2 to city 1, extend 2 by visiting nearest unvisited city, finally return to city 1. All 2's. Try all possible orderings of the points, selecting the ordering that minimizes the total length. Efficiency computes correct output quickly given input. Example, odd number problem. Input, a number n. Output, yes if n is odd, no if n is even. Which of the following algorithm is most efficient? Count up to that number from 1 and alternate naming each number as odd or even. Factor the number and see if there are any 2's in the factorization. Keep a lookup table of all numbers from 0 to the maximum integer. Look at the last bit or digit of the number. All algorithms must satisfy the following criteria. Input. There are 0 or more quantities that are externally supplied. Output. At least one quantity is produced. This figure shows the algorithm gets legal input and produce correct output by set of rules. Definiteness. Each instruction is clear and unambiguous. Finiteness. If we trace out the instructions of an algorithm, then for all cases, the algorithm terminates after a finite number of steps. Effectiveness. Every instruction must be basic enough to carry it out. It also must be feasible. Describing algorithms. Natural language. Instructions must be definite and effectiveness in human-level language such as English, Chinese. Graphic representation. Flowchart work well only if the algorithm is simple and small. Example for the flowchart is shown here. Pseudocode. Pseudocode is a description of an algorithm that is more structured than usual prose but less formal than a programming language. Pseudocode hides program design issues. Readable instructions must be definite and effectiveness in combined form of English and C or C++. Example, finding the maximum element of an array. Algorithm array max of a, n. Input an array A storing n integers. Output the maximum element in A. Current max equal to A of 0. For I equal to 1 to n minus 1, do if current max less than A of I, then current max equal to A of I, return current max. Mathematics review. Logarithms and exponents. Properties of logarithms. Log xy base b equal to log x base b plus log y base b. Log of x by y base b equal to log x base b minus log y base b. Log x power a base b equal to a log x base b. Log a base b equal to log x base a by log b base a. Properties of exponentials. A power b plus c equal to a power b and a power c. A power bc equal to a power b whole power c. A power b by a power c equal to a power b minus c. B equal to a power log b base a. Bc equal to a power c into log b base a. Floor. Floor of x equal to the largest integer less than or equal to x. Ceiling. Ceiling of x equal to the smallest integer greater than or equal to x. Summations. Summation of I equal to s to t, f of I equal to f of s plus f of s plus 1 plus f of s plus 2, it goes up to f of t, where f is a function, s is the start index and t is the end index. Geometric progression. F of I equal to a power I, given an integer n0 and a real number 0 less than a not equal to 1. Summation of I equal to 0 to n, a power I equal to 1 plus a squared up to a power n equal to 1 minus a power n plus 1 by 1 minus a. Geometric progressions exhibit exponential growth. Arithmetic progressions. An example, summation of I equal to 1 to n, I equal to 1 plus 2 plus 3 plus up to n equal to n squared plus n by 2. Two visual representations for arithmetic progression is shown in this figure. Solving recurrence equations. A recurrence is an equation or inequality that describes a function in terms of its value on smaller inputs. For example, the worst case running time T of n of the merge sort procedure by the recurrence. T of n equal to theta of 1 if n equal to 1. 2t of n by 2 plus theta of n if n greater than 1, whose solution we claimed to be T of n equal to theta of n log n. For example, a recursive algorithm might divide subproblems into unequal sizes, such as 2 by 3 to 1 by 3 split. If the divide and combine steps take linear time, such an algorithm would give rise to the recurrence. T of n equal to T of 2n by 3 plus T of n by 3 plus theta of n. Subproblems are not necessarily constrained to being a constant fraction of the original problem size. For example, a recursive version of linear search would create just one subproblem containing only one element fewer than the original problem. Each recursive call would take constant time plus the time for the recursive calls it makes, yielding the recurrence t of n equal to t of n minus 1 plus theta of 1. 3 methods for solving recurrences. That is, for obtaining asymptotic theta or big O bounds on the solution, the substitution method, guess a bound and then use mathematical induction to prove our guess correct. The recursion tree method converts the recurrence into a tree whose nodes represent the costs incurred at various levels of the recursion. We use techniques for bounding summations to solve the recurrence. The master method provides bounds for recurrences of the form t of n equal to a t of n by b plus f of n, where a greater than or equal to 1, b greater than 1, and f of n is a given function. Such recurrences arise frequently from the above equation, a divide and conquer algorithm that creates a subproblems, each of which is 1 by b, the size of the original problem, and is which the divide and combine steps together take f of n time. To use the master method, you will need to memorize 3 cases. But once you do that, you will easily be able to determine asymptotic bounds for many simple recurrences. Technicalities in recurrences. In practice, we neglect certain technical details when we state and solve recurrences. For example, if we call merge sort on n elements, when n is odd, we end up with subproblems of size, floor of n by 2 and ceiling of n by 2. Neither size is actually n by 2 because n by 2 is not an integer when n is odd. Technically, the recurrence describing the worst case running time of merge sort is really t of n equal to theta of 1 if n equal to 1, t of ceiling of n by 2 plus t of floor of n by 2 plus theta of n if n greater than 1. Boundary conditions represent another class of details that we typically ignore. Since the running time of an algorithm on a constant sized input is a constant, the recurrences that arise from the running times of algorithms generally have t of n equal to theta of 1 for sufficiently small n. Consequently, for convenience, we shall generally omit statements of the boundary conditions of recurrences and assume that t of n is constant for small n. For example, we normally state recurrence as t of n equal to 2t of n by 2 plus theta of n, without explicitly giving values for small n. The reason is that, although changing the value of t of 1 changes the exact solution to the recurrence, the solution typically doesn't change by more than a constant factor, and so the order of growth is unchanged. When we state and solve recurrences, often omit floors, ceilings, and boundary conditions. The substitution method for solving recurrences. The substitution method for solving recurrences comprises 2 steps. Guess the form of the solution, use mathematical induction to find the constants, and show that the solution works. Substitute the guessed solution for the function when applying the inductive hypothesis to smaller values. This method is powerful, but we must be able to guess the form of the answer in order to apply it. Use the substitution method to establish either upper or lower bounds on a recurrence. As an example, let us determine an upper bound on the recurrence. T of n equal to 2t of floor of n by 2 plus n, which is similar to recurrences. The solution is T of n equal to big O of n log n. The substitution method requires us to prove that T of n less than or equal to Cn log n for an appropriate choice of the constant C greater than 0. Start by assuming that this bound holds for all positive m less than n, in particular for m equal to flow of n by 2, yielding T of flow of n by 2 less than or equal to C of flow of n by 2 log flow of n by 2. Substituting into the recurrence yields T of n less than or equal to 2 of C flow of n by 2 log flow of n by 2 plus n. Finally, it gives less than or equal to Cn log n, where the last step holds as long as C greater than or equal to 1. Mathematical induction requires us to show that our solution holds for the boundary conditions. Showing that the boundary conditions are suitable as base cases for the inductive proof. Choose the constant C large enough so that the bound T of n less than or equal to Cn log n works for the boundary conditions as well. This requirement can sometimes lead to problems. Let us assume, for the sake of argument, that T of 1 equal to 1 is the sole boundary conditions of the recurrence. Then for n equal to 1, the bound T of n less than or equal to Cn log n yields T of 1 less than or equal to C1 log 1 equal to 0, which is at odds with T of 1 equal to 1. Consequently, the base case of our inductive proof fails to hold. We can overcome this obstacle in proving an inductive hypothesis for a specific boundary condition with only a little more effort. For example, we take advantage of asymptotic notation requiring us only to prove T of n less than or equal to Cn log n for n greater than or equal to n naught, where n naught is a constant that we get to choose. Keep the troublesome boundary condition T of 1 equal to 1, but we remove it from consideration in the inductive proof. First, observing that for n greater than 3, the recurrence does not depend directly on T of 1. Thus, we can replace T of 1 by T of 2 and T of 3 as the base cases in the inductive proof, letting n naught equal to 2. With T of 1 equal to 1, we derive from the recurrence that T of 2 equal to 4 and T of 3 equal to 5. We can complete the inductive proof that T of n less than or equal to Cn log n for some constant C greater than or equal to 1 by choosing C large enough so that T of 2 less than or equal to C2 log 2 and T of 3 less than or equal to C3 log 3. Making a good guess. There is no general way to guess the correct solutions to recurrences. Guessing a solution takes experience and occasionally creativity. Use some heuristics to help you and use recursion trees to generate good guesses. If a recurrence similar to one you have seen before, then guessing a similar solution is reasonable. As an example, consider the recurrence T of n equal to 2T of flow of n by 2 plus 17 plus n, which looks difficult, but because of the added 17 in the argument to T on the right-hand side. Intuitively, however, this additional term cannot substantially affect the solution to the recurrence. When n is large, the difference between flow of n by 2 and flow of n by 2 plus 17 is not that large. Both cut n nearly evenly in half. Consequently, make the guess that T of n equal to big O of n log n, which can verify as correct by using the substitution method. Another way to make a good guess is to prove loose upper and lower bounds on the recurrence and then reduce the range of uncertainty. For example, start with a lower bound of T of n equal to omega of n for the recurrence. Since have the term n in the recurrence and prove an initial upper bound of T of n equal to big O of n square. Then we can gradually lower the upper bound and raise the lower bound until we coverage on the correct asymptotically tight solution of T of n equal to theta of n log n. Subtleties. Sometimes correctly guess an asymptotic bound on the solution of recurrence, but somehow the math fails to work out in the induction. The problem frequently turns out to be that the inductive assumption is not strong enough to prove the detailed bound. If you revise the guess by subtracting a lower order term when you hit such a snag, the math often goes through. Consider the recurrence T of n equal to T of flow of n by 2 plus T of ceiling of n by 2 plus 1. We guess that the solution is T of n equal to big O of n and try to show that T of n less than equal to Cn for an appropriate choice of the constant C. Substituting our guess in the recurrence, we obtain T of n equal to Cn plus 1, which does not imply T of n less than or equal to Cn for any choice of C. We might be tempted to try a larger guess, say T of n equal to big O of n square. Although we can make this larger guess work, our original guess of T of n equal to big O of n is correct. In order to show that it is correct, however, we must make a stronger inductive hypothesis. We overcome our difficulty by subtracting a lower order term from our previous guess. Our new guess is T of n less than or equal to Cn minus d, where d greater than or equal to 0 is a constant. We now have T of n becomes less than or equal to Cn minus d, as long as d greater than or equal to 1. As before, we must choose the constant C large enough to handle the boundary conditions. The recursion tree method for solving recurrences. You can use the substitution method to prove a solution to a recurrence is correct, but it has trouble coming up with a good guess. Drawing out a recursion tree based on the analysis of the merge sort recurrence. Use recursion trees to generate good guesses. In a recursion tree, each node represents the cost of a single subproblem somewhere in the set of recursive function invocations. Sum the costs within each level of the tree to obtain a set of per level costs, and then we sum all the per level costs to determine the total cost of all levels of the recursion. A recursion tree is best used to generate a good guess, which you can then verify by the substitution method. When using a recursion tree to generate a good guess, you can often tolerate a small amount of sloppiness, since you will be verifying your guess later on. If you are very careful when drawing out a recursion tree and summing the costs, however, you can use a recursion tree as a direct proof of a solution to a recurrence. We will use recursion trees directly to prove the theorem that forms the basis of the master method. For example, let us see how a recursion tree would provide a good guess for the recurrence. T of n equal to 3t of flow of n by 4 plus theta of n square. Start by focusing on finding an upper bound for the solution, because we know that flows and ceilings usually do not matter when solving recurrences. Create a recursion tree for the recurrence T of n equal to 3t of n by 4 plus Cn square. Having written out the implied constant coefficient C greater than 0. The following figure shows how we derive the recursion tree for this recurrence. For convenience, we assume that n is an exact power of 4. Another example of tolerable sloppiness, so that all subproblem sizes are integers. Part A of the figure shows T of n, which we expand in Part B into an equivalent tree representing the recurrence. The Cn squared term at the root represents the cost of C at the top level of recursion, and the three subtrees of the root represent the costs incurred by the subproblems of size n by 4. Part C shows this process carried one step further by expanding each node with cost T of n by 4 from Part B. The cost for each of the three children of the root is C of n by 4 the whole square. We continue expanding each node in the tree by breaking it into its constituent parts, as determined by the recurrence. In this figure, Part A shows T of n, which progressively expands in Part B to Part D to form the recursion tree. The fully expanded tree in Part D has height log n base 4. It has log n plus 1 base 4 levels. Because subproblem sizes decrease by a factor of 4 each time we go down one level, we eventually must reach a boundary condition. How far from the root do we reach 1? The subproblem size for a node at depth I is n equal to 4 power I. Thus, the subproblem size hits n equal to 1 when n by 4 power I equal to 1, or equivalently when I equal to log n base 4. Thus, the tree has log n plus 1 base 4 levels at depths 0, 1 up to log n base 4. Next, we determine the cost at each level of the tree. Each level has 3 times more nodes than the level above, and so the number of nodes at depth I is 3 power I. Because subproblem sizes reduce by a factor of 4 for each level we go down from the root. Each node at depth I for I equal to 0, 1, up to log n minus 1 base 4 has a cost of C of n by 4 power I the whole square. Multiplying, we see that the total cost overall nodes at depth I for I equal to 0, 1 up to log n minus 1 base 4 is 3 power I. C of n by 4 power I the whole square equal to 3 by 16 the whole power I Cn square. The bottom level at depth log n base 4 has 3 power log n base 4 equals n power log 3 base 4 nodes, each contributing cost T of 1, for a total cost of n power log 3 base 4 T of 1, which is theta of n power log 3 base 4. Since we assume that T of 1 is a constant, now we add up the cost's overall levels to determine the cost for the entire tree is shown here. This last formula looks somewhat messy until we realize that we can again take advantage of small amounts of sloppiness and use an infinite decreasing geometric series as an upper bound. Backing up one step, we have is shown here. Thus, we have derived a guess of T of n equal to big O of n square for our original recurrence. T of n equals 3t of flow of n by 4 plus theta of n square. In this example, the coefficients of Cn square form a decreasing geometric series, and the sum of these coefficients is bounded from above by the constant 16 by 13. Since the root's contribution to the total cost is Cn square, the root contributes a constant fraction of the total cost. In other words, the cost of the root dominates the total cost of the tree. In fact, if big O of n square is indeed an upper bound for the recurrence, then it must be a tight bound. The first recursive call contributes a cost of theta of n square, and so big omega of n square must be a lower bound for the recurrence. Use the substitution method to verify that our guess was correct. That is, t of n equal to big O of n square is an upper bound for the recurrence. T of n equal to 3t of flow of n by 4 plus theta of n square. To show that t of n less than or equal to dn square for some constant d greater than 0. Using the same constant c greater than 0 as before, we have where the last step holds as long as d greater than or equal to 16 by 13 into c. In another more intricate example, the figure shows the recursion tree for t of n equal to t of n by 3 plus t of 2n by 3 plus big O of n. Omit flow and ceiling functions for simplicity. C represent the constant factor in the big O of n term. Add the values across the levels of the recursion tree shown in this figure. Get a value of Cn for every level. The longest simple path from the root to a leaf is n implies 2 by 3n, implies 2 by 3n base 2, implies goes up to, implies 1. Since 2 by 3n base k equal to 1, when k equal to log n base 3 by 2. The height of the tree is log n base 3 by 2. Intuitively, expect the result to the recurrence to be at most the number of levels times the cost of each level, or big O of Cn log n base 3 by 2 is equal to big O of n log n. This figure shows only the top levels of recursion tree. However, and not every level in the tree contributes a cost of Cn. Consider the cost of the leaves. If this recursion tree were a complete binary tree of height log n base 3 by 2, there would be 2 log n base 3 by 2 equal to n log 2 base 3 by 2 leaves. Since the cost of each leaf is a constant, the total cost of all leaves would then be big theta of n log 2 base 3 by 2, which, since log 2 base 3 by 2 is a constant strictly greater than 1, is little omega of n log n. This recursion tree is not a complete binary tree, and it has fewer than n log 2 base 3 by 2 leaves. Moreover, as we go down from the root, more and more internal nodes are absent. Consequently, levels toward the bottom of the recursion tree contribute less than Cn to the total cost. Work out an accurate accounting of all costs, but remember that we are just trying to come up with a guess to use in the substitution method. Let us tolerate the sloppiness and attempt to show that a guess of big O of n log n for the upper bound is correct. Use the substitution method to verify that big O of n log n is an upper bound for the solution to the recurrence. Show that t of n less than or equal to dn log n, where d is a suitable positive constant. We have as long as d greater than or equal to c over log 3 minus 2 by 3. Thus, did not need to perform a more accurate accounting of costs in the recursion tree. The master method for solving recurrences. The master method provides a cookbook method for solving recurrences of the form t of n equal to a t of n by b plus f of n, where a greater than or equal to 1 and b greater than 1 are constants, and f of n is an asymptotically positive function. To use the master method, you will need to memorize 3 cases, but then you will be able to solve many recurrences quite easily. The recurrence t of n equal to a t of n by b plus f of n describes the running time of an algorithm that divides a problem of size n into a subproblems each of size n by b, where a and b are positive constants. The a subproblems are solved recursively, each in time t of n by b. The function f of n encompasses the cost of dividing the problem and combining the results of the subproblems. For example, the recurrence arising from Strachan's algorithm has a equal to 7, b equal to 2, and f of n equal to theta of n square. As a matter of technical correctness, the recurrence is not actually well defined because n equal to b might not be an integer. Replacing each of the a terms t of n by b with either t of flow of n by b or t of ceiling of n by b will not affect the asymptotic behavior of the recurrence. The master theorem. The master method depends on the following theorem. Let a greater than or equal to 1 and b greater than 1 be constants. Let f of n be a function and let t of n be defined on the non-negative integers by the recurrence t of n equal to a t of n by b plus f of n, where we interpret n by b to mean either flow of n by b or ceiling of n by b. Then t of n has the asymptotic bounds which is shown below. Before applying the master theorem to some examples, let us spend a moment trying to understand what it says. In each of the three cases, we compare the function f of n with the function n power log a base b. Intuitively, the larger of the two functions determines the solution to the recurrence. If, as in case 1, the function n power log a base b is the larger, then the solution is t of n equal to theta of n power log a base b. If, as in case 3, the function f of n is the larger, then the solution is t of n equal to theta of f of n. If, as in case 2, the two functions are the same size, we must multiply by a logarithmic factor and the solution is t of n equal to theta of n power log a base b into log n equal to theta of f of n log n. In the first case, not only must f of n be smaller than n power log a base b, it must be polynomially smaller. That is, f of n must be asymptotically smaller than n power log a base b by a factor of n power epsilon for some constant epsilon greater than 0. In the third case, not only must f of n be larger than n power log a base b, it also must be polynomially larger and in addition satisfy the regularity condition that af of n by b less than or equal to cf of n. This condition is satisfied by most of the polynomially bounded functions that we shall encounter. Note that the three cases do not cover all the possibilities for f of n. There is a gap between cases 1 and 2 when f of n is smaller than n power log a base b, but not polynomially smaller. Similarly, there is a gap between cases 2 and 3 when f of n is larger than n power log a base b, but not polynomially larger. If the function f of n falls into one of these gaps, or if the regularity condition in case 3 fails to hold, you cannot use the master method to solve the recurrence. Using the master method. To use the master method, we simply determine which case, if any, of the master theorem applies and write down the answer. As a first example, consider t of n equal to 9t of n by 3 plus n. For this recurrence, we have a equal to 9, b equal to 3 and f of n equal to n. And thus we have that n power log a base b equal to n power log 9 base 3 is equal to theta of n square. Since f of n equal to big O of n power log 9 minus epsilon base 3, where epsilon equal to 1. We can apply case 1 of the master theorem and conclude that the solution is t of n equal to theta of n square. Now consider t of n equal to t of 2n by 3 plus 1, in which a equal to 1, b is equal to 3 by 2 and f of n equals 1 and n power log a base b equal to n power log 1 base 3 by 2 equals n power 0 is equal to 1. Case 2 applies since f of n equal to theta of n power log a base b equal to theta of 1 and thus the solution to the recurrence is t of n equal to theta of log n. For the recurrence t of n equal to 3t of n by 4 plus n log n, a equal to 3, b equal to 4, f of n equal to n log n and n power log a base b equal to n power log 3 base 4 is equal to big O of n power 0.793. Since f of n equal to big omega of n power log 3 plus epsilon base 4, where epsilon is approximately equal to 0.2. Case 3 applies if we can show that the regularity condition holds for f of n. For sufficiently large n, we have that a f of n by b equal to 3 into n by 4 log n by 4 less than or equal to 3 by 4 n log n is equal to c f of n for c equal to 3 by 4. Consequently, by case 3, the solution to the recurrence is t of n equal to big theta of n log n. The master method does not apply to the recurrence t of n equal to 2t of n by 2 plus n log n. Even though it appears to have the proper form a equal to 2, b equal to 2, f of n equal to n log n and n power log a base b equal to n. Vectors and matrices. Vectors. A vector is a one-dimensional array of numbers. For example, x is a vector of size 3 is shown here. N vector, sometimes called a vector of length n and n vector. We use lowercase letters to denote vectors and we denote the ith element of a size n vector x by xi for I equal to 1, 2 and up to n. Addition of two vectors. If two vectors u and v have the number of components, their sum u plus v is the vector obtained by adding corresponding components from u and v. U plus v is equal to u1, u2 and up to un plus v1, v2 and up to vn is equal to u1 plus v1 plus u2 plus v2 and up to un plus vn. Multiplication of a vector by a scalar. The product of a scalar k and a vector u, that is ku, is the vector obtained by multiplying each component of u by k. Ku is equal to k of u1, u2 up to un is equal to ku1, ku2 up to kun. Here we define minus u is equal to minus 1 into u and u minus v is equal to u plus of minus v. K into u plus v is equal to ku plus kv. K is a scalar and u and v are vectors. Column vector. The standard form of a vector to be as a column vector equivalent to an n cross 1 matrix. Example, x is equal to 2, 3 and 5. Row vector. Row vector is obtained by taking the transpose of column vector equivalent to an 1 by n matrix. Example, x transpose is equal to 2, 3 and 5 in row order. Unit vector ei is the vector whose ith element is 1 and all of whose other elements are 0. Usually, the size of a unit vector is clear from the context. Matrices. Matrix is a rectangular array of numbers. For example, the matrix A is shown here. It is a 2 by 3 matrix. A is equal to Aij, where for I equal to 1, 2 and j equal to 1, 2 and 3. We denote the element of the matrix in row I and column j by Aij. We use uppercase letters to denote matrices and corresponding subscripted lowercase letters to denote their elements. We denote the set of all m by n matrices with real valued entries by r power m by n, and in general the set of m by n matrices with entries drawn from a set S by S power m by n. The transpose of a matrix A is the matrix A power T obtained by exchanging the rows and columns of A. The transpose of the given matrix A is shown here. Zero matrix is a matrix all of whose entries are 0. Such a matrix is often denoted 0, since the ambiguity between the number 0 and a matrix of zeros is usually easily resolved from context. If a matrix of zeros is intended, then the size of the matrix also needs to be derived from the context. Square matrices. Square n by n matrices arise frequently. Several special cases of square matrices are of particular interest. Diagonal matrix has Aij is equal to 0. Because all of the off-diagonal elements are 0, we can specify the matrix by listing the elements along the diagonal. The example for diagonal matrix is shown here. Identity matrix. The n by n identity matrix In is a diagonal matrix with ones along the diagonal. In is equal to diagonal of 1, 1 up to 1. The example is shown here. When I appears without a subscript, we derive its size from the context. The ith column of an identity matrix is the unit vector Ei. Tri-diagonal matrix T is one for which Tij equal to 0 if modulus of I minus j greater than 1. Non-zero entries appear only on the main diagonal. Immediately above the main diagonal, Ti plus 1 for I equal to 1, 2 up to n minus 1, or immediately below the main diagonal, Ti plus 1, Ti for I equal to 1, 2 up to n minus 1. The tri-diagonal matrix is shown here. Upper triangular matrix U is one for which Uij. All entries below the diagonal are 0 is shown here. An upper triangular matrix is unit upper triangular if it has all ones along the diagonal. Lower triangular matrix L is one for which Lij equal to 0 if I less than j. All entries above the diagonal are 0 is shown here. A lower triangular matrix is unit lower triangular if it has all ones along the diagonal. Permutation matrix P has exactly 1 1 in each row or column and zeros elsewhere. An example of a permutation matrix is shown here. Such a matrix is called a permutation matrix because multiplying a vector x by a permutation matrix has the effect of permuting, rearranging the elements of x. Symmetric matrix A satisfies the condition A equal to A transpose. Example for a symmetric matrix is shown here. Basic matrix operations. The elements of a matrix or vector are numbers from a number system such as the real numbers, the complex numbers, or integers modulo a prime. The number system defines how to add and multiply numbers. We can extend these definitions to encompass addition and multiplication of matrices. Matrix addition. If A equal to Aij and B equal to Bij are m by n matrices, then their matrix sum C equal to Cij is equal to A plus B is the m by n matrix defined by Cij equal to Aij plus Bij for I equal to 1 to m and j equal to 1 to n. That is, matrix addition is performed component-wise. A zero matrix is the identity for matrix addition. A plus 0 equal to A equal to 0 plus A. If lambda is a number and A equal to Aij is a matrix, then lambda A equal to lambda Aij is the scalar multiple of A obtained by multiplying each of its elements by lambda. As a special case, we define the negative of a matrix A equal to Aij to be minus 1 and A equal to minus A, so that the ijth entry of minus A is minus Aij. Thus, A plus of minus A equal to 0 equal to minus A plus A. Matrix subtraction. A minus B equal to A plus of minus B. Matrix multiplication. Start with two matrices A and B that are compatible in the sense that the number of columns of A equals the number of rows of B. If A equal to Aik is an m by n matrix and B equal to Bkj is an n by p matrix, then their matrix product C equal to AB is the m by p matrix C equal to Cij, is shown here. For I equal to 1 to m and j equal to 1 to p. To multiply n by n matrices, square matrix multiply performs n cube multiplications and n square n minus 1 additions, and so its running time is theta of n cube. Matrices have many of the algebraic properties typical of numbers. Identity matrices are identities for matrix multiplication. IMA equal to AIN equal to A for any m by n matrix A. Multiplying by a zero matrix gives a zero matrix A into 0 equal to 0. Matrix multiplication is associative. A into BC equal to AB into C. For compatible matrices A, B and C, matrix multiplication distributes over addition. A into B plus C equal to AB plus AC. B plus C into D equal to BD plus CD. For n greater than 1, multiplication of n by n matrices is not commutative. For example, if A equal to 0, 1, 0, 0 and B equal to 0, 0, 1, 0, then AB equal to 1, 0, 0, 0 and BA equal to 0, 0, 0, 1. Matrix vector products are vector-vector products. If the vector were the equivalent n by 1 matrix, thus if A is an m by n matrix and X is an n vector, then AX is an m vector. If X and Y are n vectors, then X transpose Y equal to summation of I equal to 1 to n Xi Yi. Is a number actually a 1 by 1 matrix called the inner product of X and Y. The matrix XY transpose is an n by n matrix Z called the outer product of X and Y with Zij equal to Xi Yj. The Euclidean norm double mod of X of an n vector X is defined by double modulus of X equal to x1 square up to xn square the whole power 1 by 2 equal to X transpose X 1 by 2. Thus, the norm of X is its length in n-dimensional Euclidean space. Basic matrix properties. Matrix inverses, ranks and determinants. The inverse of an n by n matrix A to be the n by n matrix denoted A inverse, such that A into A inverse equal to In equal to A inverse A. For example, the example is shown here. Many non-zero n by n matrices do not have inverses. Non-invertible or singular matrix. A matrix without an inverse is called non-invertible or singular matrix. An example of a non-zero singular matrix is shown here. Invertible or non-singular matrix. If a matrix has an inverse, it is called invertible or non-singular matrix. Matrix inverses, when they exist, are unique. If A and B are non-singular n by n matrices, then B A power minus 1 equal to A inverse and B inverse. The inverse operation commutes with the transpose operation. A inverse transpose is equal to A transpose inverse. The vectors x1 to xn are linearly dependent if there exist coefficients c1 to cn, not all of which are 0, such that c1x1 plus c2x2 up to cnxn equal to 0. The row vectors x1 equal to 1, 2 and 3, x2 2, 6, 4 and x3 4, 11, 9 are linearly dependent. For example, since 2x1 plus 3x2 minus 2x3 is equal to 0. If vectors are not linearly dependent, they are linearly independent. For example, the columns of an identity matrix are linearly independent. The column rank of a non-zero m by n matrix A is the size of largest set of linearly independent columns of A. Similarly, the row rank of A is the size of the largest set of linearly independent rows of A. A fundamental property of any matrix A is that its row rank always equal its column rank, so that we can simply refer to the rank of A. The rank of m by n matrix is an integer between 0 and min of m, n, inclusive. The rank of 0 matrix is 0 and the rank of n by n identity matrix is n. An alternate but equivalent and often more useful definition is that the rank of a non-zero m by n matrix A is the smallest number R such that there exist matrices B and C of respective sizes m by R and R by n such that A equal to BC. A square n by n matrix has full rank if its rank is n. An m by n matrix has full column rank if its rank is n. The ijth minor of an n by n matrix A for n greater than 1 is the n minus 1 by n minus 1 matrix A ij, obtained by deleting the ith row and jth column of A. The determinant of an n by n matrix A recursively in terms of its minus by the determinant A, which is shown here. The term minus 1 power I plus j, determinant of Aij, is known as the cofactor of the element Aij. Modulus of A, determinant of A, is shown here, where an n by n array of numbers enclosed by straight lines is called a determinant of order n. N by n array of numbers enclosed by straight line is not a matrix but denotes the number that the determinant function assigns to the enclosed array of numbers, that is, the enclosed square matrix. The determinant of order 1 is modulus of A11 equal to A11. The determinant of order 2 is shown here. The determinant of order 3 is shown here. An important property of the determinant function is lemma. For any two n-square matrices A and B, determinant of AB equal to determinant of A and determinant of B. The lemma says that the determinant function is multiplicative. An important point in invertible matrices and determinant, the lemma says a square matrix is invertible if and only if it has a non-zero determinant. Worst case and average case analysis. Analyzing an algorithm. The process of determining how much resources are used by a given algorithm. Resources such as memory, communication bandwidth, and computer hardware, but most often measures computational time. Able to make quantitative assessments about the goodness of one algorithm compared to another, and do this without implementing and running an executable version of an algorithm. Before analyzing an algorithm, must have a model of the implementation technology that we will use, including a model for the resources of that technology and their costs. 3 types of analysis. The worst case running time of an algorithm is the function defined by the maximum number of steps taken on any instance of size n. The best case running time of an algorithm is the function defined by the minimum number of steps taken on any instance of size n. The average case running time of an algorithm is the function defined by an average number of steps taken on any instance of size n. Best, worst, and average case comparison chart is shown here. Drawbacks of average case analysis. Based on a probability distribution of input instances, the distribution may not be appropriate. Provides little consolation if we have a worst case input. More complicated to compute than worst case running time. Worst case running time is often comparable to average case running time. Worst case analysis. Much simpler to compute as we do not need to average performance on many inputs. Instead, we need to find and understand an input that causes worst case performance. Provides guarantee that is independent of any assumptions about the input, often reasonably close to average case running time. The standard analysis is performed. Random Access Machine (RAM model). In RAM model, instructions are executed one after another without concurrent operations. Should define the instructions of the RAM model and their costs. Must be careful not to abuse the RAM model. For example, what if a RAM had an instruction that sorts? Then we would sort in just one instruction. Such a RAM would be unrealistic, since real computers do not have such instructions. How real computers are designed these instructions? The RAM model contains instructions commonly found in real computers. Arithmetic such as add, subtract, multiply, divide, remainder, floor, ceiling. Data movement, load, store, copy, and control, conditional and unconditional branch, subroutine call, and return. Each such instruction takes a constant amount of time. The data types in the RAM model are integer and floating point for storing real numbers. RAM model analysis are usually excellent predictors of performance on actual machines. Analyzing even a simple algorithm in the RAM model can be a challenge. Case study: analysis of insertion sort. Input size depends on the problem being studied. For many problems, such as sorting or computing discrete Fourier transforms, the most natural measure is the number of items in the input. For example, the array size n for sorting. For many other problems, such as multiplying two integers, the best measure of input size is the total number of bits needed to represent the input in ordinary binary notation. Sometimes it is more appropriate to describe the size of the input with two numbers rather than one. For instance, if the input to an algorithm is a graph, the input size can be described by the numbers of vertices and edges in the graph. Input size measure is being used with each problem. Running time of an algorithm on a particular input is the number of primitive steps are executed. A constant amount of time is required to execute each line of our pseudocode. One line may take a different amount of time than another line, but we shall assume that each execution of the ith line takes time Ci, where Ci is a constant. This viewpoint is in keeping with the RAM model, and it also reflects how the pseudocode would be implemented on most actual computers. The insertion sort procedure with the time cost of each statement and the number of times each statement is executed for each j equal to 2, 3 up to n, where n equal to a. Cost and times of each statement in insertion sort procedure is shown in this figure. The running time of the algorithm is the sum of running times for each statement executed. A statement that takes Ci steps to execute and executes n times will contribute Cin to the total running time. To compute T of n, the running time of insertion sort on an input of n values, sum the products of the cost and times columns. Obtaining is shown here. Even for inputs of a given size, an algorithm's running time may depend on which input of that size is given. For example, in insertion sort, the best case occurs if the array is already sorted. For each j equal to 2, 3 up to n, find that a of I less than or equal to key in line 5, when I has its initial value of j minus 1. Thus, Tj equal to 1 for j equal to 2, 3 up to n, and the best case running time is shown here. Express this running time as an plus b for constants a and b that depend on the statement costs Ci. It is thus a linear function of n. If the array is in reverse sorted order, that is, in decreasing order, the worst case results. We must compare each element a of j with each element in the entire sorted subarray a of 1 to j minus 1, and so Tj equal to j for j equal to 2, 3 up to n. Summation of j equal to 2 to n, j equal to n of n plus 1 by 2 minus 1, and summation of j equal to 2 to n, j minus 1 equal to n into n minus 1 by 2. The worst case running time of insertion sort is shown here. Express this worst case running time as an squared plus bn plus c for constants a, b and c that again depend on the statement costs Ci. It is thus a quadratic function of n. In insertion sort, the running time of an algorithm is fixed for a given input. In analysis of insertion sort, at both the best case, in which the input array was already sorted, and the worst case, in which the input array was reverse sorted, the longest running time for any input of size n, finding only the worst case because 3 reasons are there for this orientation. The worst case running time of an algorithm gives us an upper bound on the running time for any input. It provides a guarantee that the algorithm will never take any longer. For some algorithms, the worst case occurs fairly often. For example, in searching a database for a particular piece of information, the searching algorithm's worst case will often occur when the information is not present in the database. In some applications, searches for absent information may be frequent. The average case is often roughly as bad as the worst case. Suppose that we randomly choose n numbers and apply insertion sort. How long does it take to determine where in subarray a of 1 to j minus 1 to insert element a of j and average half the elements in a of 1 to j minus 1 are less than a of j and half the elements are greater. On average, therefore, we check half of the subarray a of 1 to j minus 1 and so Tj is about j by 2. The resulting average case running time turns out to be a quadratic function of the input size, just like the worst case running time. The scope of average case analysis is limited because it may not be apparent what constitutes an average input for a particular problem. Often, assume that all inputs of a given size are equally likely. In practice, this assumption may be violated, but we can sometimes use a randomized algorithm which makes random choices to allow a probabilistic analysis and yield an expected running time. Order of growth. Used some simplifying abstractions to ease our analysis of the insertion sort procedure. First, ignored the actual cost of each statement, using the constant Ci to represent these costs. Expressed the worst case running time as an an squared plus bn plus c for some constants a, b and c that depend on the statement costs Ci. Thus, ignored not only the actual statement costs but also the abstract cost Ci. Make one more simplifying abstraction. It is the rate of growth or order of growth of the running time that really interests us. Consider only the leading term of a formula, example an square. Since the lower order terms are relatively insignificant for large values of n, ignore the leading term's constant coefficient. Since constant factors are less significant than the rate of growth in determining computational efficiency for large inputs. For insertion sort, when ignore the lower order terms and the leading term's constant coefficients, left with the factor of n square from the leading term. Write that insertion sort has a worst case running time of theta of n square. Usually consider one algorithm to be more efficient than another if its worst case running time has a lower order of growth. Due to constant factors and lower order terms, an algorithm whose running time has a higher order of growth might take less time for small inputs than an algorithm whose running time has a lower order of growth. But for large enough inputs, a theta of n squared algorithm, for example, will run more quickly in the worst case than a theta of n cube algorithm. Conclusion. In this chapter, we have covered the following in detail. Mathematics for algorithmic sets, functions, relations, vectors and matrices, linear inequalities and linear equations. Review of basic concepts, worst case and average case analysis, big O notations, small o notations, omega notations, theta notations, solving recurrence equations.